Alrighty, hello everyone. Good afternoon, at least where I am here on the East Coast. Good afternoon, everyone. My name is Cory Phillips, and I'm a program director here at ARPA-E. Actually, I just celebrated my 1-year anniversary yesterday, and it's been quite an exciting year. On behalf of our agency director, the Honorable Dr. Evelyn Wang, as well as the federal employees here and the contractors at the agency, I really thank you for attending this webinar on catalytic application testing for accelerated learning chemistries via high-throughput experimentation and modeling efficiently. This is a program we call CATALCHEM-E. So the purpose of this webinar is really to provide some general information and context around the CATALCHEM-E program. This webinar is really to help those individuals and teams who want to apply to this program and pursue funding, really help clarify some things. So my plan is really to stay very close to the language that we published in the Notice of Funding Opportunity, what we call the NOFO, previously called the FOA, Funding Opportunity Announcement. But since this is a quiet period, I'm going to make sure I stay close to that language, but provide the context so you can understand the way I think about this program. I'll spend a few minutes covering some general background information regarding the agency, because I realize that for many of the folks, at least in the catalysis community, and maybe even the acceleration community on the US side, you haven't had ARPA funding, or this is like the first time you've been interacting with ARPA-E. So I want to give you sort of like an agency DNA kind of like presentation, so you really understand what we're looking for. We're a little different than other federal agencies and the way we fund and why we fund. And I want you to know about that and learn about that. So I'll spend a little time there. And then from there, I'll move into some general topics about the program and highlight a lot of our responses to certain frequently asked questions that we've had. You know, I'm not trying to sort of read the NOFO to you. You can read that on your own, but I do want to touch on some things that maybe are between the lines that we could clarify. And then I think the payoff for you today will be that you should understand a lot better ARPA-E's approach to funding and how we manage research projects, as well as our intention with this CATALCHEM-E program. And then your call to action, I think, is for you to gather your teams, influence how you decide to pull teams together, and structure your concept paper submissions at a very high quality that are aligned with both the agency and CATALCHEM-E's missions and objectives. I do want to thank the team here. First, actually the webinar team, I'm not listing here by pictures, but Cindy, as well as the comms team, thank you so much for setting up this webinar here today and working with me in the background to make sure I was prepared. On our catalysis team, our AI catalysis team, or our CATALCHEM-E team, we have 2 other fellow employees that were involved on the tech to market side. And I'll tell you a little bit more about what tech to market means to ARPA-E. It's a big deal, really what separates us from a lot of other agencies. But Stephanie King and Kirk Liu, both who've, Kirk worked for a process technology company in the past, UOP, and Stephanie had experience with Haldor Topsol. So we have folks that have dealt with industrial process design and catalysis. Libby Archel, who's my AI/ML SME on the team, and Robbie Habley, who's many of you have met him with the workshop development, but he has a background in reaction engineering as well, and he's worked for BASF in their catalysis division as well. And then Mervyn Zhao, who's brought a lot of experience with us with particle and materials understanding and synthesis information. So knowledge, that's been great. And then we have a tech council that are actually other program directors and leadership that actually help us sort of frame the opportunity and get it to the point where it's able to be pitched as an idea for the agency. So I want to acknowledge them as well. And I want to acknowledge the other program directors, we call them PDs, program directors, that were involved in workshops and helping us out along the way, giving us advice. It's really been great to see everyone stand behind this opportunity, because this is a first for the agency, and then definitely all of the team here at Booz Allen that's involved in helping us get programs developed. So thank you to all. So CATALCHEM-E was announced last month by Director Wang. And she supported this initiative by funding us $35 million. We're very excited about this opportunity to showcase communities that I have very high regard for. This will be the first program dedicated to the application of catalysis in the agency's 15-year history. And it's highlighting the catalysis, acceleration, and modeling communities, and given a platform to take a scientific risk in an area that really is important. But more important than that is the scientific risk of bringing these communities together and working at the interface of all of these three groups, which I think is pretty exciting. So in the press release, we highlighted, in particular, the self-driving labs as a material acceleration platform. However, we're keenly aware that there are other experimental techniques and hardware for performing high-throughput testing, as we indicated in the NOFO. And this program really combines these communities together to explore, create a method, a tool. It's about really creating this method that can accelerate, and then taking that method and then allowing it to serve in a discovery capacity. The agency mission is really to overcome the long-term and high-risk technological barriers in the development of energy technologies. So in the case of CATALCHEM-E, the energy technology is twofold. One is a commercial-ready manufacturable, what we call technical catalyst, whether you're doing thermochemical, technique, or electrochemical, but a catalyst that is within an environment and in a form that is of a commercial-ready form. And then the AI-based accelerated workflow methodology. So there are two key technologies, energy technologies that are being developed. But the five categories, are important for us. We were stood up in 2008, 2009 timeframe by Congress to really deal with the importing issue that we had at the time. It was with fossil energy and oil, but we've kept that as part of our mission: reducing imports, reducing emissions, improving efficiency, improving how we manage radioactive waste, and then of course infrastructure and energy infrastructures. In fact, one of my colleagues just released a program, DC Grids, that deals with enhancing America's infrastructure. So we try to stay aligned with these missions. So you can easily see how we structured the program here at CATALCHEM-E. Really, you can see where reducing emissions, the net zero 2050 emissions theme kind of resonates throughout the NOFO. And then, of course, there's opportunities for improving efficiency with catalyst improvements. You can have less process steps. You can have higher yields, which reduce the separation, downstream separation intensity, or reducing the recycle streams, things like that. So there's opportunities for catalysis to impact the overall process design. So there's also a desire to ensure that the U.S. has some technical leadership, of course, in key areas. So this is kind of like our overall mission. But if you've never written a proposal to ARPA-E, this is a message here that I really want you to hear in this sort of diagram here, where on the y-axis I have like a cost per performance or over a particular time or scale, comparing existing methods or heuristics with the ARPA heuristic. And really, ARPA-E is all about disruptive and transformative approaches relative to like the incumbent ways of doing things. So in CATALCHEM-E, we're challenging the traditional paradigm in developing catalytic materials by bringing together the expertise, tools, and perspectives from several different communities. And if we can develop a new learning curve, we can move a lot faster, we could de-risk faster, and we can move catalytic materials into the commercialization phases quicker. This does not mean that we're getting rid of the traditional fundamental scientific method that's involved in fundamental catalysis research, which is the underpinning of which we've stood up so many processes, the chemical processes and petrochemical processes and refining processes because of that method. But we're trying to enhance this method. One thing to point out, though, ARPA-E, and this is important when you are developing concept papers, and for those of you that are moving on to full applications, this is not incremental research here at ARPA-E, so this is important. This is transformative research approaches, not incremental research approaches like you do find maybe in more fundamental funding agencies. So it's important because we work hand in hand with those other agencies. So we need fundamental incremental research to always continue here in our country. And what ARPA-E does is we complement that by actually providing disruptive approaches that enable fundamental research to move into paths that commercialize it faster. And so it's really a complement. So it's not one or the other. They both work together. So I keep up with my colleagues at BES and NSF. I stay in touch with my colleagues there that are doing catalysis work, doing acceleration work, and doing AI/ML work, because it's important that we continue to fuel each other's research interests. It's important that we make this distinction. And I want you to know that when you're writing your concept papers and writing your proposals, taking the technology risks that would end up helping everyone in the long run, all the stakeholders, but sometimes other agencies don't want to take. So you can see we have a number of programs throughout the portfolio over the years, and we take pride in naming our programs. I'm sure you can probably look at the name that I've selected here, CATALCHEM-E. I tend to refer to catalysis as surface alchemy. And so that was part of the origin of that name. But we have some other fun names along the way. And we've sort of selected things we can put most of our programs, even our alumni programs in our active programs, in terms of like electricity generation and efficiency in transportation. But I do think there's another bin or pillar that will be established here with CATALCHEM-E. And I think it's a pillar that can be referred to as energy materials. And CATALCHEM-E will be the first sort of program to sort of bust open the door for this opportunity for the agency to spread its wings in these energy materials. And it's cross-cutting. Energy materials kind of cross-cuts around a number of different things. But I'm excited about what this community here will be able to do in the future and showcase what is capable by this community to the agency. So that's really exciting. We did have one program out of all of our programs listed here that was focused on AI, ML, long before we had the LLM kind of revolution come in. And it was back in April 2019, we released a program called Differentiate, and it was really incorporating machine learning into energy technology and product design processes, really kind of enhancing the creativity of the hypothesis generation process, helping engineers to kind of develop new concepts, doing like more inverse design. And so we've taken some elements from that and incorporated in our program here in CATALCHEM-E. But this fourth pillar, we're really excited about this energy materials eventually in the future. We will actively, in terms of our process, we will actively try to manage and steward and usher any project that we funded into follow-up funding, whether it's internal, external, private, VC foundations. We're invested in your success. We're kind of like almost like a pre-seed investor, but not officially. And so as we go through our phases here, where we define programs and we have the competition phase, which is what we're in right now, when people are writing proposals and teams are writing proposals, then teams get awarded, and then we do what we call active management. And that's something that's a little different than other agencies, the way we do this. We're taking the risk together. These are not grants that we give. We actually go into what's called cooperative research agreements. And so these CRADAs, if you will, these are the way that we decide that we're going to take risks together. We negotiate what those risks look like and those milestones for those risks. And then we decide together the goal and change science and discover something great. And then after a few years, the project eventually is successful, and then we're ready to, figure out how to take this successful team and move them hopefully into something that resembles more commercialization. Closer to commercialization, we've de-risked quite a few things. So we want to always walk with our projects and usher them to the next phase. It's not just like we fund you and that's it, we're done. No, you're part of our story. You're part of the ARPA-E narrative, and we want to see your success from the time we fund you all throughout. So that's important. And so because of that philosophy, we've had some really interesting and impressive impact across the industry and with our metrics. So we've invested, since our beginning, over almost $4 billion, or over 1,500 projects. And we've generated, just in private sector funding, $12.6 billion. But then we've had 30 exits from a lot of the companies that were started. Over 150 companies started, and those exits have valuations over $20 billion. So when you talk about the the return on investment from any industry. And I came out of industry. I worked in oil and gas for almost 17 years. These are metrics that any oil and gas exec would be thrilled in seeing. So any executive in any industry would be thrilled to see. And so it's really impressive as an agency. 360 projects, and we've had over 7,500 peer-reviewed journal articles, 1,100 patents we supported, and a lot of licenses, over 400 licenses. So these are the types of things. So you can see in your project, and as you start to think about what you're proposing, keep these metrics in mind that you're part of this story where we're very vested and interested in how the outcome of your technology will manifest in the marketplace. And we've been building on, from the start on the foundation of DARPA. Many of you are familiar with the DARPA model, but really the tech to market piece of ARPA-E is really what differentiates our agency. It's not an add-on section in your proposal, where you just have to kind of check it off. Oh, we're just gonna, this include the tech to market or commercialization, or we're too early stage research. We don't know how this looks in the future. No, that's not how ARPA-E works. We're very interested in what the path looks like if this works. If this high-risk work that we're funding, that we've agreed that we're going to invest together in, if it works, will it matter? Will it be impactful? And what is the path to commercialization? So please keep that in mind when you're writing. So we will seriously evaluate what is your technology offering to the marketplace, because this is the cornerstone of our agency. It's what makes us different, taking these early stage research and talking about the path to commercialization all in the same breath, and being very serious about it. It's not just a paper exercise. So we're very proud of that, and that's part of our success, our formula for success. For our performers, this is kind of like how we fit in throughout the sort of DOE's kind of like R&D continuum, if you will. We want to see, for our performance, we want to see our technology commercialized and come out of the R&D cycle. So we try to facilitate as much as possible connections with other DOE agencies within the DOE ecosystem and outside with external investors as well. So you see, we're early stage. If you want to use the TRL model, you can. And you can see where we fit into that TRL model. But we really try to engage I'm always, talking to my colleagues across the DOE, and also giving them insight on teams and projects that are interesting, that they may be interested in funding with their programs as technology matures and develops. So the technology development shouldn't just stop with us once the program ends. No, it's just the beginning of hopefully a great story to tell. And just to kind of give you all some timeline. So right now we're at the full release. And if we kind of call this T equals 0, we would say usually in terms of like getting into awards and negotiations, we're sitting at about 8 months generally in the past. And we're doing things to sort of streamline that as much as we can now, but just in general, until we start negotiations. So awards announced about 8 months later. But this gives you kind of the range of what happens, with concept paper, people writing concept papers and reviewing them, then full apps, and then reviewing a few apps. It takes generally what we've seen, that kind of time so you can get an idea of what it looks like now based on where we're sitting now in the schedule. And then once again, getting back to our life cycle. So many of you on the call today, we started off with a phone call where we were just sort of envisioning what this concept CATALCHEM-E really looked like. And so we reached out, and that's our envision stage. We engaged, and we invited you to a workshop. We pitched within the agency and got program approval. And then we started developing our NOFO. That's where we're in now. This is kind of called the quiet period, if you will. And then we would go and establish, contracts, awards 8 months later, and then we execute the project. So even if you're not on a project team and you're not getting awarded, there are ways to support any program that you're interested in helping out with. And so even at the envision stage, you can take part in workshop calls and respond to RFIs. You can go on our teaming partner page and register as a partner. You can support our scale-up projects as a financial partner, or serve as an external reviewer. You can join one of our advisory boards. And of course, you can attend some of our annual meetings to programs. So each program has annual meetings that they usually kick off when the program starts. So you have a kickoff of these annual meetings, and then every year the PIs meet up and the teams. So there are ways to also stay engaged in our ecosystem, even if you're not funded as a project team. And so just to kind of give you a flavor, it really takes organizational diversity to do the type of research that we do generally in ARPA-E, but definitely for CATALCHEM-E, it's no different. And so far, there's been more academic and sort of small business functions leading a lot of the work, followed up by the nonprofits and large corporations. But this is based on our data, aggregate data over the past. It doesn't mean that teams should be organized with this type of distribution to sort of ensure success. That's not the point. The point is it just means that a significant number of projects are led by each type of organization. The application process is open to all. And I'm sure this distribution will shift and morph as we continue with our years of running the agency. And so what really makes a good ARPA-E project? So I've covered a lot of this in the previous slides, but in summary, really what makes a good ARPA-E project is that impact. Can we see a path to market? Hit at least two of our mission areas in a major way that I mentioned. Two, will it challenge the status quo? How is your proposed catalyst development workflow going to transform, accelerate accelerate relative to the current workflow that we've been doing for the last 100 years? Does the project bridge your project sort of bridge a white space and to investigate a white space that there's little research or funding in, or nothing at all has been funded, or no one's really looked at all? And is there a cross-discipline team that can hit the ground running with the right resources and know-how? So this is what program directors like myself, along with the other reviewer community, this is what we're trying to assess. When we look at project proposals, are they hitting on all these cylinders here? All right, so let's chat a little bit about the program. So, it took, I like to start off with the discussion about Haber-Bosch. It's one of the most successful catalysis stories that we've had. And it's pretty impactful. But for me, particularly in this program, CATALCHEM-E, so I like to sort of start here. And so one of the earliest stories of this brute force, high throughput parallel testing took place in the discovery of what we call the modern iron-based Haber-Bosch catalyst. Alwyn Mintosh, the chemist that was over that, ran over 20,000 experiments over a number of years, and it was conducted on a trial and error basis, and using intuition and judgment as the feedback to kind of guide what the next compositional space looks like. What's interesting, we're still continuing to optimize on this chemistry 100 years later, just to demonstrate the vast parameter space in composition and structure in catalysis. So catalysis is just a very elegant and very difficult branch of science. And so it takes this level of commitment. But what I like about this story is that because of these high throughput experimentation, and this was done in parallel, by the way. So we're talking about 100 years ago, parallel testing. So here's an example where parallel testing really influenced our population growth. Here's a figure that shows, the population over time, and the green is what the population would have been if we had not had the ammonia from this reaction serve as fertilizer, and how it helped the population. And so what I'm really coming to you today as a community, a set of communities here on this call, I'm saying, well, this parallel testing is not necessarily that new. We've done it 100 years ago. Now you just need to put computer science to it and put some intelligence to it, because we have that available. Haber didn't have that available at the time, and Bosch, they did not. Alwyn did not have that. We do. And we also have the ability to have automation capabilities, both hardware and software. So we have some tools that they didn't have. And it's because of this initial high throughput experimental work 100 years ago that life on the planet was impacted. So I'm asking now, we have another existential sort of issue facing us right now with climate change. And I'm asking you as the community to come with me to do something special again for catalysis to have an impact on life on the planet. It's a high probability that Bosch would have received high marks on my impact criteria if ARPA-E was back 100 years ago, because it definitely had impact. It's sort of like the movie, if you all are fans of the Avengers movies, I'm sort of like Tony Stark, and I'm calling all my superhero friends, you, to come with me and figure out if we now can help with this next crisis that we're facing. But what's hard? It's hard because what I'm asking here is to go across scales. We're not just stopping at traditionally what we would call a research catalyst, and which is the powder form, where we're looking at very fundamental structure and issues and associated with powders and trying to get to the active site and understand the active site. We actually want to structure it and give it an engineered form because we want that potential for success at the commercial scale. So we're pushing the research to go all the way to technical catalyst scale. So both for electrochemical and thermochemical, what that looks like. And so it takes a long time to do this. We know this. And not only does the computational work take a long time to do the simulations, if you want to do fundamental simulations, but the actual experiments and testing for developing a real catalyst material across length scale, it takes a long time, and there's a lot of valleys of opportunities. So we think this is what will make the entire program so very impactful overall. The parameter space remains huge for structure and composition, but now we have the capability to assist and how we navigate through this space, which really includes composition, structure, and surface coverage, the things that matter. But if you do all of that, just looking at biometallics in a space, a relatively wide space here, there's so many permutations that just a single researcher, it's very difficult to go over the space for a single researcher. So this is why we need the tools. We need tools that can not only cross length scales, but also that can help us with that large space. And so we're looking at both tracks here, thermochemical and electrochemical, looking at the microstructures, we're looking at the structures even at the atomic scale, figuring out how we can bring all of this information again into one setting and one environment and manage that information. So manage the characterization information, manage the testing information across scales for our own advantage in terms of the modeling that needs to take place with the learning models. So we think that if we do this properly, we can definitely cut things down. And we're calling this our Archimedes operator. We're calling this Archimedes catalysis because we're leveraging all of these themes of high throughput screening and testing, parallel testing, advanced characterization, and even modeling reactors across the continuum using multiphysics and of course the AI, and bringing it all together where traditional research, we can cut that 10 years or 15 years down to 1 year, 1.5 years. So this is really the premise behind it. And so, if we look at the program itself, the big objectives here when you look across, starting with trying to figure out what the compositional space is for to get a good set of research catalysts started, and then characterizing those, and then moving those into a down-selected group of technical catalysts that you sort of scale up and you test at some engineered relevant scales, or when I say industrial relevant, I'm sort of like engineering relevant scales that start to matter in terms of modeling and simulation. So you can imagine a larger device, something that can scale up. This cycle here gets interesting, and really the key objectives is, can we synthesize these new drop-in manufacturable sort of technical catalysts at kilogram scale for both thermochemical and electrochemical reactor systems, and then really look at these catalysts under realistic conditions. Now, we know that it's really tough to get feed streams that are exactly what they will be in the future, but realistic conditions could include if you have a feed stream that has impurities in it, but you're sure that feed stream will have some type of cleanup and pre-treatment before a reactor upstream, then you can include that in your TEA analysis, or you have a process design, a basic process design that says, okay, I'm gonna have some upstream pre-treatment, and just make sure that the impurities that at least exist after that pre-treatment are mimicked. That's realistic conditions, at least from the feed stream perspective. And also another key objective is really to develop these AI-enabled sort of closed loop workflows, acceleration workflow topologies. So for these future reference chemistries, they are used to validate these workflows, and there will be other impact in the phase 2 of the program where you take the tool that you developed in phase 1, and now you have this novel catalyst, the novel tool that now you can go out and look at novel catalyst reaction discoveries and co-designs with this acceleration tool that you can do a lot faster. Once again, imagine if Bosch had this CATALCHEM-E tool that you all will develop here in this program. Imagine if you could have given your tool here to Bosch and Alwyn 100 years ago, what that would look like. It would be incredible. They would have done that in probably months. And then, of course, the sort of third objective is really to generate these AI-ready searchable databases. The databases will be critical for us moving forward as a community by combining and pre-processing high-quality, multi-scale, multimodal data as you generate it from synthesis, characterization, and performance. So, we want all of the data. So that's what we're showing here in this illustration. It's really all of that, not just one part. So even if you're dealing with fundamental first principle calculations, how that impacts synthesis, and what are the control knobs in synthesis that really relate back to the structural information that you have at fundamentals, at the first principles, modeling and simulation. So we're trying to connect synthesis to this in certain ways. So that's important. And we're really not interested in sort of chasing and verifying like spreadsheets that are tucked away in 100 different locations. We're really these databases really should be professional, delivered sort of organized and leveraged, so they can be leveraged basically in the future by future data scientists and modeling. So that's important. And so this field is really exploding right now. We believe it's on the cutting edge, and it's reflected by the growth in the published literature. And we expect that this program will really also contribute to this knowledge explosion by creating more journal articles, reports, and patents, white papers, position papers, business plans, you name it. So we're excited about that. The program is also designed to be interdisciplinary, so that one entity can't do everything. Given the timeline and resources, teams must hit the ground running and leverage each other's abilities and resources. I posted here the teaming list that you can get on. And so essentially, we put that out there. We brought together over 10 different sub communities to create this one new community that really is defined by these sort of three thrusts here. And I'm excited to really showcase this new community through the lens of the high risk, high reward ARPA-E framework. Here's an example of what we call like an example workflow that was provided in the NOFO. It's not necessarily the baseline workflow on how you may understand it, this traditional catalysis work, and it's not specific to any reference chemistry, which you will have to make it specific when you write your proposals. But it's a guide to kind of give you an idea of how you represent a topology, and it can be even more granular than this. So you can add, if you want to add more symbols to your legend to represent other areas that we may have missed when we put this together. But our point here was to say, hey, there's rational discovery over here with research powders, and then there's sort of traditional sort of more what we would call more industrial catalysis on this side. And between the two, there's always experts in the loop on both sides at every phase. And so we believe that, as you take experts out of the loop with the artificial intelligence piece, that not only do things get faster, but then also this handshake that happens between technical catalysts and research catalysts when you move into industrial scale. This handshake is more seamless, whereas if you had 10 years of sort of starting from concept all the way through to commercial ready material, you can cut that down quite a bit. So we want you to propose the way you see this baseline workflow and how you will impact this flow, or basically relative to this baseline workflow, how your proposed workflow will improve it. And these are very simplified workflow topologies here, but just to give you an idea, so you may have a traditional serial workflow is like here in the corner up here in the upper right, but then you might have a combinatorial that includes combinatorial sort of throughput driven, but it includes still the design, make, test, and analyze piece of it. You might have a self-driving sort of workflow here. And then it may be something more of a rational design where you start off with more combinations, more ab initio kind of combinations from predictions, and then you move into some more validation, and then you have to go back and still close the loop. So closing the loop is a big deal, but these are simplified sort of general topologies. We are interested in topologies. And then also there's reference chemistries that were provided in the NOFO. The twofold purpose of the reference chemistry is the purpose is twofold. One is method validation. So a big part of this program is about the phase one. It's about developing a accelerated method, accelerated workflow. So if you're developing a workflow method, you need a reference. You always need a known value if you're developing any method or anything. So this is our way of saying, here's the known value, okay? And so we try to accommodate, the phase of the feed as well as electrochemical and thermochemical. The second purpose of this is really to accelerate, to basically validate that you can accelerate. So if you have the proper initial guess, not too narrow, not too wide, but something in between that allows you to first sort of get some compositional space, provide some, input, at least maybe structurally, but at least compositionally, this kind of gets you an initial guess that once you get around and you go around that closed loop and you get to the point where you can now your model can predict a new compositional space, the time that it takes for you to rediscover the actual known reference catalyst that is attached to that reference chemistry, that time, the time it takes for your model to predict that composition, that is really the rediscovery validation. And really that defines acceleration. For instance, if you take one of these reactions here, this let's just say the CO2 to methanol, say it, you came up with your baseline workflow is 10 years or whatever, that you researched that and it took that long, and then you were able to show, and you have the actual real catalyst that you're showing here, you were able to show that you could discover that composition and structure within a few months experimentally, and then your model was able to do that. This is really what that's about. So that's the reference chemistry approach. That's what the purpose of that. So we try to include gas, liquids, mixed feeds for both electrochemical and thermochemical. We try for the electrochemical just to say which reference in terms of the electro is more important in terms of you actually matching the performance. So for the PM, so the water splitting, it would be the anode, so that would be the OER there for that, and so that part, that anode reaction is where you would have the performance metrics to match based on our metrics table. And for like here, I'm saying the tags here, these triglycerides, we just showed an example here of a triglyceride, just to give an example, but you could have a number of different triglycerides that you're considering, plant, animal, UCL, etc. So the whole point of reference chemistry is to have chemistries that have some type of commercial connection, where you can actually have the information on the performance of the catalyst for this chemistry, as well as the material itself, and then the information about the composition and structure of that material, because that's what you have to validate. And just to kind of comment a little more on metrics. So in terms of level of automation, we expect some things in your workflow may not be automated. So that's why that was sort of like a 90%, but we don't want to restrict teams either with our own bias in terms of like what automation means and doesn't. So automation does not mean autonomous, but autonomous does encompass automation. Automation also includes analytical measurement data, maybe into a cloud or any way you manage that automated, but data from analytical instruments and any data pre-processing and wrangling and model and having that all automated. That's what that sort of means. Catalyst performance is the list that we mentioned here. This is no way an exhaustive list. This is not encompassing what we mentioned here. These are just sort of some frontline metrics that we mentioned to kind of to spur you along. But we want, as an expert, if you're applying to this program, you're proposing, we want to make sure that you let us know that you understand what metrics are used to characterize catalysts when they're in reactors. So things like carbon utilization could be something that you're interested in, or cyclophotometry curves, and many other metrics that are listed here. Please include all the relevant metrics to demonstrate your knowledge and expertise and whether you're having a thermochemical or electrochemical system that you're testing. We purposely did not include all the metrics here. This is not limited to the ones mentioned, so it's not exhaustive. We didn't want to, do the work of writing a proposal for you, but we wanted to see what you are going to say about what's important metrics to monitor. And of course, the 90% of the commercial benchmark, so that reference chemistry has a commercial catalyst attached to it. So you'll need to have access to both the material, the characterization, and performance data for that material. And this material doesn't have to be the latest generation. It could be regarded still as an industry benchmark. Maybe years ago, it's not the, so there may not be an issue per se with your partner, whoever you're getting the material from, or how you're accessing that material, as long as it is an industrial benchmark. I think that's important. On the AI ML side, I think this is a couple of metrics here. We're talking about composition and characterization data coming together and into an input vector to predict performance in the forward model. So, you may have spectral X-ray, surface or bulk data along with composition data, and can you now predict the performance based on that data? And then the opposite in the inverse, where it becomes a one-to-many problem in the inverse design. So we tried to provide some language there to help, without being too prescriptive, to help people think about how the predictions would work. And of course, you still need your reference catalyst and information to help with that, but you also need an additional second catalyst to help validate that work. And we talk about that in the NOFO. On the discovery side, once you have your tool, we tried to scope out the areas where we think are like interesting research area and potentially interesting for us and you as well. We want you to make the case on if you go outside of what we think are research and potentially interested in areas on why that is. But more importantly, it's about now you have the tool in phase 2. Now go out and do something special, do something disruptive, do something transformative with that tool. So that's why we've highlighted the areas where it's potentially unknown or potentially interesting, because we want to explore. This is ARPA-E, so we want to go out and disrupt and explore. So real quick, I just want to make sure that we do have foreign work waivers, but there's an exception. International subrecipients, it's kind of case-to-case basis that we look at that. So look at our FAQ that we've answered on that. Rediscovery, and it's important that when you talk about rediscovery and verification, that your initial guess in terms of composition space should be reasonably wide, not like a few elements. We want to be able to showcase that your model actually can now crawl and hunt throughout compositional space and structural space to actually do the job that it needs to, that to enhance what humans have been doing over the last 100 years. In technical calcs, we've asked to be synthesized in kilogram batches, but the testing can be done in tens to hundreds of grams. So we know there's a lot of expense that's involved in testing, but you can test hundreds of grams, tens of hundreds of grams, but it needs to be at the point where you can actually now have some level of modeling attached to that to help with that. And then, of course, on the closed loop, I just want to mention we have a strong interest in inverse design approaches where you can take that sort of pilot scale testing as inputs into the inverse design problem. So this is definitely new and exciting for all of us here on the call to actually do this. And so we're interested in seeing how you do that. So I'll close by saying, if it works, will it matter? That's what we're going to know. This has always been the focus of an ARPA-E project, but the ultimate goal is to get it to the marketplace. And so even in the marketplace, who will buy it? What are the barriers? Who's going to fund all this? Who will make it? How long will it last? Who will copy it? How will it be obsolete? These are sort of things you think about as well. So with that, I will stop. Thank you for your time and attention. And please use our inbox if you have any questions. And I look forward to seeing you help me change the world and join me in my Tony Sparks impression as superheroes. Take care and have a good holiday.